Hello, this is the Math 135, Module 3, Section 5.1 video content. This is not going to be covered in class, but it will be something that you are going to be required to know, and it will be assessed in homework, quizzes, and exam. So this is kind of just a foundational kind of prereq to the course, something that you would have seen either in high school or in a previous math course that came before Math 135. So we're going to jump right in. It's linear inequalities in two variables. So throughout the course so far, we've really been focused on the equations with the equal signs. And we're now going to switch gears and kind of look at inequalities, linear inequalities. So to graph a linear inequality in two variables, so x and y, we first need to discuss some new vocabulary or terminology. So a line will divide a plane into two regions. So we know when we draw a line, we have our whole coordinate plane. If you draw the line, it goes on forever in both directions, and that will actually split our coordinate plane into two separate planes, what we call half planes. A vertical line will divide it very specifically into a left half plane and a right half plane, because notice it is completely up and down. So you have a whole, everything on this side is to the left of the blue line, everything on this side is to the right. If your line is horizontal or slanted, so maybe positive slope or a negative slope, your boundary line, which is what we call the line that splits those into the half planes, it will have an upper and a lower half plane. Now, how you determine that, the easiest way to see it is to find the y-intercept where you cross the y-axis. So that's this one that goes up and down. When you find that point, which this one specifically is at 0, 0, anything that is above that, so if we travel up the y-axis, so following that line all the way up, anything in that side or that region, that's called the upper half plane. If we're at our y-intercept and we travel down the y-axis, anything on that side is what we call the lower half plane, okay? Our four different inequality symbols that we can see when we're graphing linear inequalities are less than, greater than, less than or equal to, and greater than or equal to. So these first two are what we call the ones that exclude the boundary line. So less than and greater than are graphed with excluded boundary lines. That means the boundary line is not part of our solution, which means, because remember, when you're graphing, the whole visual of a graph is you're graphing the solutions or the information that is true in our statement. So all of our answers here, so say this lower half plane was our solution in this specific one, we would be saying that every ordered pair in that specific half plane makes our inequality true. So that's what we mean when we're saying we're graphing the solution. And then the boundary line could also technically be part of the solution or not. It's just like when we were graphing on just an x-axis, when we were doing inequalities where they just shade to the left or to the right, it was just number line. You had like open and closed circles. Remember, that meant either you included the endpoint or you did not include the endpoint. So open circle was not included and closed circle was included. So less than and greater than are kind of like that open circle concept. So we are going to use a dashed line to represent the boundary line because it's not part of the solution. We get really close to it, but it's not included. If we have the less than or equal to or the greater than or equal to in our statement, then we're going to be including the boundary line as part of our solution. So we're going to be using a solid line. So I'm going to also underline the words included and excluded, just to make sure we drive that point home, okay? So what are our steps for actually graphing a linear inequality? Well, step one, you're going to graph the boundary line. So you're going to graph the equation that is corresponding to our inequality. In other words, we're just swapping the less than, greater than, less than or equal to, or greater than or equal to for an equal sign and graphing it just like we learned how to graph lines. Remembering to use a dashed line if the inequality is not included, or a solid line if the equality is included. Then we will choose a test point anywhere in the plane, so they mean in one of the half planes, essentially, that is not on our boundary line. We're going to substitute those coordinates into the inequality, and then at step 3, we'll be making a determination about that. But the origin will make a really easy computation for you if it's available. That means it's not on the boundary line. So if 0, 0 is on your boundary line, you can't use it as your test point. If the test point satisfies the original inequality, then we'll shade the half plane that contains the test point, because that whole region that has the test point in it would have been a true set of solutions. So every single ordered pair in that half plane would have given me a true. if the test point does not satisfy the original inequality, in other words, we get a false statement when we plug in our test point. That means every point on that side is actually false. So we need to shade the opposite half plane, okay? So we're going to do two examples of this before we move on to a little bit more involved concept. So graph the inequality. We have 2x plus 3y equals 6. So step one is that we're supposed to look at that as the boundary line. So the boundary line would be if it had an equal sign instead of the less than. So 2x plus 3y equals 6. And then I always like to make a note before I get too far into this, whether this is going to indicate dashed or solid. This one will be a dashed boundary line because we do not have that equal to sign. Now, there's two ways you can actually graph this boundary line. You could solve it for y, which would put you into the y equals mx plus b format. That's called slope intercept. And that really is nice because it gives you the slope and the y-intercept. Sometimes, though, it gives you some nasty fractions to deal with. Just depends on if the numbers divide nicely. Another way you can do when you're in standard form, which is what this is, we have our ax plus by equals c, is you can find the x and y-intercepts. Sometimes you won't be able to use this method, but I want to show you on this one because it does work out nicely. And then on the next example, I'm going to show you the other method. So if you want to find your x-intercept, you're going to plug in 0 for y. So that's going to be 2x plus 3 times 0 equals 6. That'll just be 2x equals 6 or x equals 3 if we divide both sides by 2. But that is not just x equals 3. It is an ordered pair because we plugged in 0 for y. So that would be 3, 0. That's our x-intercept. If we want to get our y-intercept, we plug in 0 for the x. So that's going to be 2 times 0 plus 3y equals 6. So that would just be 3y equals 6. Always be careful. Make sure you check what that sign is right there. Divide both sides by 3. We get y equals 2. Again, that's an ordered pair, though, with 0 for x. Remember, x always comes first, and 2 for y. So I'm going to go over here to the side and graph those 2 points. And remember, draw a dashed line. That's going to be my boundary line. So 0, 2 is right here on the y-axis. 3, 0 is on the x-axis, and we're going to be drawing the best dashed line we can through those points. It's always nice if you have a ruler handy, which I do not. Doing the best that I can. It's not perfectly straight, but that's pretty good for by hand. Now, you're going to choose a test point. I usually write down what my test point is, but I also like to label it on my graph when I'm doing this by hand. So since 0, 0 is not on the boundary line, I can use that as my test point. And I'll just write TP as a note for test point. So we're going to plug that in to our inequality, the original inequality. So 2 times 0 plus 3 times 0 less than 6. That's going to be 0 plus 0, so that's just 0 less than 6. Now that statement, this is actually starting part 3, is true because 0 is less than 6. So we're going to shade the test point half plane. I'm going to use my highlighter for this part. So since we got a true on this side, that means every single ordered pair all the way up to the boundary line, if I plugged any of those into my inequality, I would get a true statement. So if you checked, say, 1, 0 or -2, -2, any of those that you plug in should all satisfy the inequality where the left side is going to be less than 6. Okay. All right, let's look at my next example. This one is one where you could also move this over when you go to do your boundary line. So let's put this in equation form. Notice I'm also going to write myself a note that this indicates that I'm going to have a solid, not a dashed line, a solid line because we have the equal to. Now, if I move that over, thinking, okay, let's do that same thing with x and y intercepts. That'll be nice and easy. So just add the 5y over to the left side. Now I'm in ax plus by equals c format. The only problem with this is if you go to solve both of these, you're going to get 0, 0 because this only has one intercept. It goes through the origin, so it has the same x and y intercept at 0, 0. For a line, you need exactly 2 points to be able to define the line, so we have to have a second point. So you could do a table of values to find that second point, or if you have one like this where you don't see a constant term, sometimes just solving for y equals mx plus b gets you there a little quicker. So I'm going to go ahead and solve this for y equals mx plus b. And we'll use that slope-intercept form to graph it. So to solve it for that, we have to get y by itself. So that's going to be 5y equals negative x. Divide both sides by 5. So that's going to be negative 1/5 x. And then you can write plus 0 if you want to see your b, because it doesn't actually exist there. So this is my y-intercept, which also matches with what I saw when I was talking about if I'd done the intercept method. It's 0, 0. And then my slope is negative 1/5. Now, you have two options for this. You can put the negative on top, so you could go down 1 and then right 5. Or if you put the negative on the bottom, you would be going up 1 and then left 5. So remember, one direction's negative, the other direction is a positive direction. So when I graph the 0, 0 over here, I don't think I want to go up 1, left 5, because I'm going to run off my graph. So I'm going to go down 1, right 5. So down 1 and then right 1, 2, 3, 4, 5. I could do that again if I had plenty of room on my graph, but mine's kind of running out of space. I will be hitting it at 10 for that next one. Okay, so this time let's pick a test point. Let's see. Maybe I'll pick one that's down here in the negatives, just to show you that you can also pick something negative when you plug it in. So let's see, the point 2, negative 2, for the y value being negative, that's in this region right here, the lower half plane. I know this is the lower half plane because here's my point on my y-axis. These values below it are in the lower half plane. I could just as easily pick positive 2, positive 2. That's in the upper half plane, or any other point. This is a personal choice, just as long as it's not on the boundary line. So notice I'm not using 0, 0 because that would have been on the boundary line. Then we're going to plug that into our inequality to see if this is true or false. So 2 for x greater than or equal to negative 5 times negative 2. That would be 2 greater than or equal to, that's going to multiply to a positive 10. That is a false statement. So since my TP is in the false region, we shade the other or opposite half plane. Okay, so get my highlighter out. I cannot shade down here because everything in this region should be false, just like this one was. So we're going to be shading above that line, which is what we call the opposite half plane to the one that the test point is in. And you do really need to remember shade everything up to the entire edge, because this goes on forever, and it that just helps us indicate that this is an infinite set of ordered pairs that are true. And remember, the boundary line is actually also true in this situation as well. That's what the equal to is allowing for. Whereas in the first example, the boundary line was not part of the solution set. Okay. So now, once we've got the basics underway of how to graph a linear inequality in two variables, we're going to start talking about application problems. And in application problems, unfortunately, there are certain situations we might need to impose upon our variables. So let's talk about this, what's called non-negative constraints. So when we're interpreting a linear inequality and we talk about non-negative constraints, that means that we're letting the x and y be positive or equal to 0. Why would we do that? Well, many times when we're solving an application problem, we need our variables to be non-negative. In other words, if x is number of cats and y is number of dogs, you can't have negative cats or negative number of dogs. That doesn't make sense in the context of the problem, because you either have no dogs, no cats, or you have a positive number of one of them. You can't have a negative number of animals. So this means we will usually need to restrict our problems to what we call the first quadrant of the coordinate plane. Now, that is what we mean by those non-negative constraints. So to do that, we say all of our x's need to be greater than or equal to 0, and all of our y's need to be greater than or equal to 0. That actually adds 2 more boundary lines and shadings to our problem, because we're actually going to be shading almost a little small system And this is the most basic system of linear inequalities. We will spend more time actually doing what we call multiple constraints, where we see not just the non-negativity, but we actually have multiple different linear inequalities that have X and Y. But to start us off, we want to just focus on, let's restrict our inequality to quadrant 1. Okay, so let's show you how that looks. So it says graph this first inequality subject to the non-negative restrictions. And this is where you're going to start seeing much larger numbers, because sometimes in our application problems, we do have to deal with large scale values. So this is 20x plus 40y is less than or equal to 1,600. And we also want to make sure that whatever x is, it's not negative, or but it can be equal to 0 and it can be positive. So that's what we call non-negative. Y also needs to be equal to 0 or positive. So we want to make sure we're in quad 1 only. First thing I always like to do when I see a problem like this is I like to reduce the inequality if possible. That just means if you see something that you can multiply or divide through by that will make the numbers smaller, that will help you when you go to label your graph and how many numbers we have to go out. So I'm going to divide this first inequality all the way across by 20, because every single term is divisible by 20. Now, do be careful if you're dividing by a negative, that will flip the direction of your inequality. So we're going to divide that first inequality by 20 just to simplify the values that we're dealing with. So 20 divided by 20 would just be x, and then 40 divided by 20 would be 2y, and then 1,600 divided by 20 is going to be 80. So this is just the simplified kind of equivalent version, remember, because we're just multiplying or dividing by a non-zero coefficient of that original inequality. So that's just going to help us out. Now, in this scenario, I like to do it by the x and y intercept method instead of the y equals mx plus b method, just because if I can easily divide these to get my x and y intercept, to me, that's just easier, because you get really quick at it. You just kind of cover the one you're zeroing out, solve for the other one. So let's do that. So x intercept, so this is for the equation. Remember, we're doing the boundary line. X plus 2y equals 80. So my x-intercept would be 80, because you're just going to get x equals 80 when you plug in that. So that's going to be 80, comma 0. My y-intercept is going to be plugging in 0 for x. So 0 plus 2y equals 80. So 2y equals 80 means that y equals 40. So that would be the point, 0, 40. Okay, so that's going to help me with my scaling down here. So I might count by tens, but maybe only label every other dash. It's up to you. Just be consistent when you count on your x-axis and be consistent when you count on your y-axis. So let's say that I'm doing by tens, but I'm going to label just every other one. So that's 20, 30, and then 40, 60, 80, 100, 120. That should be plenty for this. And then I'm going to do the same thing, since we're kind of dealing with a similar scale. 20, 40, 60, 80, 100, 120. You could just as easily try and count by, fives, 5, 10, whatever you want to do, as long as you're consistent and you get to your points that you need. So when I go to plot these, I have 80, 0. That's my x-intercept. 0, 40. That's my y-intercept. This is going to be a solid line. Like I said, do the best you can. Sometimes this pen goes a little off. So that's my line. And then I'm going to also do my non-negative constraints. I'm going to do those in different colors, so we can talk about that, because we're going to be talking about the shading next. So I've got this one, I'm going to draw the line in red. And for this one, I'm going to draw the line in, let's see, orange, maybe blue, a light blue. Okay. So x equal to 0, if you just think about x equal to 0, that is a vertical line at the x value of 0. So that's going to be right here. Actually is the y-axis. Okay. And then y equal to 0, because remember, we're just talking about the boundaries right now, is going to be a horizontal line. So y equals 0 is horizontal through the point y equals 0, which is right here on the y-axis. Okay. Now, why is that going to be important? Well, we'll talk about that after we finish graphing the purple inequality. So for our test point here, I would not use 0, 0, and you can, it's fine. But if you have like multiple lines, sometimes I like to choose something that's in between all of the lines. But since, we're just doing one inequality, you could technically do 0, 0, since these are equal to, that won't hurt anything. But I think I'm going to choose 20, 20 as my test point. Okay. So I'm going to choose that test point of 20, 20. So 20 times 20 plus 40 times 20 is less than or equal to 1,600. So 20 times 20 is 400. 40 times 20 is going to be 800. The question is 400 plus 800 less than or equal to 1,600? And it is. 1,200 is less than or equal to 1,600. So what that tells me is that in this purple inequality, we would be shading the lower half plane. Now, for the actual shading, when you go to do these on your homework, they want you to shade in consideration of the actual non-negative constraints as well. So when you talk about, so I'm going to do these little arrows. So this is going to be shading this direction. And you can do that kind of all the way down when you visualize it and all the way up. So that's what we determined when we looked at that specific test point. When you talk about x is greater than or equal to 0, you're shading, since this is a left and a right side only, the positive values are going to be greater than 0. The negative values are going to be less than 0. So we're going to be shading this direction. And you can kind of think about that all the way up and down. I'm not going to draw all of those all the way up and down, but it's all the way up and down the line. Okay. When you look at y is greater than or equal to 0, again, this is a horizontal line. So you have an upper and lower half plane, and they're distinguished by positive versus negative. So the ones that are greater than or equal to 0 are the ones above it. So this specific problem, when you see this in your homework and it says graph this, and it says subject to the non-negative restrictions, not only do they want us to shade where, the inequality that we're dealing with, the first one, is true, but also where is x and y greater than or equal to 0. So we're just shading that intersection or overlap. So that's right here in the middle. So it's this little triangle. So we want to not only be in the correct region for the 20x plus 40y is less than or equal to 1,600, but we also want to be in quadrant 1 only. That's what that x greater than or equal to 0 and y greater than or equal to 0 means. So there is my shaded region around that test point. Okay. And that would be our solution there. All right, so let's do another one like this, and then we're going to look at some actual application problems where we have to come up with the inequality ourselves. So let's look at this one. It says, we're going to graph the first inequality. That's this one again, subject to these non-negative restrictions. So if you wanted to, you could go ahead and throw the x greater than or equal to 0 on here. And we know that's going to shade this direction. And the y greater than or equal to 0 is the member of the x-axis, and we're shading above it. So we've already got those kind of in place. So this one's the blue. This one's the red. Okay. All right, so let's look at our actual inequality that has some values that are a little more interesting. So we have negative 5x plus 10y. I'm going to go ahead and think of this as, remember, an equation for a second so that I can find the boundary line. We know the boundary line is going to be solid again because we have the equal to. So we're going to do this one. I'm going to do it by the x and y intercept method just because it's easier when it's already in this format. So x and y intercepts, if we plug in 0 for y, we're going to get negative 5x equals 100. Divide by the negative 5, we get negative 20. So that's the negative 20 comma 0. And then if we have our y-intercept, we have 10y. If we plug in 0 for x equals 100. So y is going to equal to 10. So that's going to be 0, 10. So notice I have a negative x-intercept this time. So when I go to graph this, I need to be very careful where I label. I'm going to label these by 10. So this is negative 10. This line right here is negative 20. That way I can graph that as my x-intercept. And then my y-intercept is going to be 10, 20. And the reason I'm counting by these instead of counting by 1, 2, 3, 4, 5, 6, 7, 8, 9, and all that is because there was not enough in this direction to make it easy to graph that. But if you wanted to, you can kind of use this as a guide for slope. We can go up 1 over 1 or over 2. So up 1 over 2, up 1 over 2. You can kind of continue the line that way. That way you can see a better way of drawing it, since those are so close together. Okay. Now, if I was drawing this on my own paper and I didn't have a pre-made graph, I probably would have, gone further out to the left this direction. But a lot of these are going to be, remember, in the first quadrant when we're done. So the reason that we like to kind of, only draw a first quadrant graph is because of that. Now, we need to, and again, if you wanted to have done this one by y equals mx plus b instead, it might have come out a little easier to graph that way. We could have added the 5x over and then divided everything by 10. Sorry, that was supposed to be 10y. So y equals 1/2 x plus 10. So notice that's exactly what we did when I said, oh, I can see the slope here between these 2 points. It's at 10, we have our y-intercept, and we go up 1 over 2, up 1 over 2, okay? Now let's get our test point. So let's say, I want to choose, I'm going to label a few more of these, 10, 20, 30. This is 30. Let's say I want to choose the test point. Since it's greater than or equal to, my gut instinct is that maybe we're going to be up above the purple line. So maybe I want to pick a test point above here. So maybe I want to pick 20, 30 as my test point. Okay. So test point is 20, 30. We plug that in, that's going to be -5 times 20 plus 10 times 30. Is that greater than or equal to 100? Well, we've got, that would be, let's see, -100 plus 300 greater than or equal to 100. So that's going to be 200 is greater than or equal to 100. That is a true statement. Now, that means we're going to be shading, remember, above this purple line. Okay. So where do I end up shading? Well, because of this problem having the blue shading above, the red shading to the right, and the purple shading above, notice that we're only going to get this region right here. So I'll try to outline it first. We're going to have everything to the right of the red line until we get to that purple line, because remember, we're only shading above the purple line. Then we're going to go above the purple line in this direction forever. And then it would be shading everything in between, because the blue line actually is kind of, we don't ever cross the blue line until way over here into quadrant, 2 and 3. That's where we cross below the blue line. So notice the blue line, even though it doesn't look like it's doing much, if we had graphed somewhere in one of the other quadrants, it would help us determine where we're shading. But a lot of times, like I said, the X and Y non-negativity constraints are there because the variable doesn't make sense to be negative. Okay. So there is our shaded region of that first inequality with the non-negative restrictions in consideration. Okay, so let's look at what do we do if they give us a word problem and we need to come up with the inequality ourselves. So I have 2 different versions. One's a very basic one where they only give you the information you need, and the second one is going to have an extra piece where they've given you more than you need numerically wise, and you have to pick out the correct pieces. So a concert promoter wants to book a rock group for a stadium concert. A ticket for admission to the stadium playing field will cost $125. A ticket for a seat in the stands will cost $175. So notice we have 2 different types of admission tickets that they can get. The group wants to be guaranteed total ticket sales of at least 700,000. How many tickets of each type must be sold to satisfy that guarantee? So we're letting X represent tickets sold in the playing field, and Y is the number of tickets sold in the stands. Okay, so we want a ticket sale inequality. So notice the stadium price is $125. The stand price, so that's the playing field right there. The stands price is going to be $175, and then we want it to be at least 700,000. That's the keyword for how we're going to know what inequality to use. So I'm going to have that for the playing field. We're going to pay $125 for every ticket. So remember, X is all the tickets that they sell for the playing field, plus, because they're going to add that to the profits that, or the total cost, I should say, of the stand ones. The stands are $175 for every stand seat ticket. And at least means we want to come out at 700,000 or better. So that's going to be greater than or equal to 700,000. Now, in this scenario, again, I don't want to have to, use huge numbers on my graph if I don't have to. So I always triple check to see if this is reducible. And I believe we can divide everything by 25 and get nice numbers. So if we divide 125 by 25, we get 5x. If we divide 175 by 25, we're going to get 7y. And 700,000 divided by 25 is 28,000. So those numbers are a little bit easier to work with. Then we were going to write our non-negative constraints. That just means, right, the x has to be greater than or equal to 0, and the y has to be greater than or equal to 0, because remember, you can't sell a negative number of tickets. Okay, so we need to graph the boundary line for that first one. So 5x plus 7y equal to 28,000. And because that number is so big, and I'm not, you could go ahead and find the x and y intercepts, or you can do the y equals mx plus b. It's always personal choice when you get to that point. I think they're both divisible by the 5 and the 7. The 28,000, I think, will go, 5 and 7 both go evenly into it. So I'm going to go ahead and do my intercept method. So x-intercept, we're going to plug in 0 for y. So that gives me 5x equals 28,000. So when I divide, that's going to give me 5,600. That's the ordered pair, 5,600 comma 0. For the y-intercept, we're going to plug in 0 for the x. So that's going to give me 7y equals 28,000. Divide, we're going to get 4,000 for that one. So that would be 0 comma 4,000. Okay, so I always like to have that done first before I try to figure out my scale. So we need to get all the way up to 5,600, and on the y-axis, we need to get all the way up to 4,000. It looks like maybe counting by, let's see, 200, 400. I'm just counting by 200s on every tick mark. So 200, 400, 600, 800, 1,000. So every 5 is 1,000. So that'd be 1, 2, 3, 4, 2,000. 1, 2, 3, 4, 3,000. 1, 2, 3, 4, 4,000. 1, 2, 3, 4, 5,000. 1, 2, 3, 4. Yeah, that'll get us all the way up to 6,000. I always look at the graph I'm given and make sure my scale is going to work. So I'm going to mark, I'm counting by 200s, but I'm only going to, just because I don't want to squeeze too many numbers in here, I'm going to put every other marking. So really, it's going to look like I'm counting by 400s. So this would be 800. This will be 1,200. That's going to be 1,600. And then 2,000. 2,400. 2,800. We have then 3,200. And I'm going to pause and go ahead and fill the rest of this out, and then I will restart the recording just so you don't have to watch me scale all of these. Okay, so I've got my scale here on all of my parts. So notice I just counted by, technically 200s, but I just marked every other one, so it looks like we're counting by 400s. So we're going to plot, and I'm going to use a different color so this will stand out, so the lighter purple. We have a y-intercept of 0, 4,000. So that's going to be right here. We have an x-intercept of 5,600 comma 0. So that's right down here. And then we're going to want to draw a line between those. So let's do the best we can with this. Yeah, it's always better if you're able to use a ruler and not have to do it on a tablet. Okay, so there's my inequality boundary line. And notice it is solid. We marked that, well, we didn't write it, but it is going to be solid. Okay, because the equal to. All right, then we also have the x is greater than or equal to 0. So I like to do that one in red. So remember, that's just the y-axis all the way down. And we're going to be shading to the right of that. We have the y is greater than or equal to 0, which is the x-axis, and you're shading up above it. So we need to determine which direction are we shading on that magenta kind of purpley line, okay? So I'm going to pick a test point. Let's say 400, 400. That's a nice one. So test point of 400, 400. Plug that into our original inequality, which is right up here, the one we reduced down to. You can use the reduced form. 5 times 400 plus 7 times 400. Is that greater than or equal to 28,000? Well, 5 times 400 is 2,000. And then 7 times 400 is 2,800. If you add those together, that is not going to be bigger than 28,000. So that one, that test point I picked was false. That means this entire region between the red, or excuse me, under the magenta line, and that part's going to all be false. Okay. So it looks like we are shading above the magenta line. Okay. Now, when we go to highlight this, be really careful, because your instinct's to highlight everything above the magenta line. But remember, we have to stay above the blue line, to the right of the red line, and then above the magenta line for our first inequality. So what you're going to see is that we actually have kind of, it looks like we're shading like a regular inequality, but we have those non-negative constraints that are keeping us from shading the rest of this half plane on those edges. And then we would continue to shade all of this. Okay. So they've got to sell any combination of tickets in the yellow highlighted region. Now, what does that mean? So that means, if you interpret this, if they sell, let's say, let's look at 4,000 for X, and let's say 3,200 for Y. So let's talk about that point right there, just so you can get the actual, what have we done? So 4,000 and then 3,200, that's this point. According to what I shaded, that should be a true solution. So if you plug that into the inequality, they should be making more money than this inequality that we've reduced down to, so more than 28,000, which would then, remember, correlate up to that more than 700,000 that we originally started with, because we just divided everything by 25. So if we plug that in, 5 times 4,000, that's 20,000, plus 7 times 3,200, that's going to give me a total of 42,400. So they would be above that 28,000 there. Okay. So every single point in this yellow shaded region is true for our inequality of ticket sales and the non-negative constraints. Okay. All right. Last one. So this one has a textile mill uses 2 blended yarns. So we have a standard blend. And then if you notice a little bit further down, we have a deluxe blend. Now, they're giving us a lot of information in these specific problems. Sometimes they'll tell us like a bunch of stuff about one type and then a bunch about the other type. So notice we have in the standard, we have 30% acrylic, 30% wool, and 40% nylon, okay? And in the deluxe blend, we have 9% acrylic, 39% wool, and 52% nylon. And they're going to use those blends to produce various fabrics. How many pounds of each yarn should the mill use to produce a fabric that is at least 20% acrylic? Okay. So we have to come up with, first of all, what are our X and our Y? Well, X and Y, if they're saying how many pounds, that means that we have how many pounds of the standard blend did they use and how many pounds of the deluxe blend did they use. The question doesn't really focus on the wool or the nylon composition of these at all. We are looking specifically for a constraint related to the acrylic inequality part, okay? So you need to note that on this specific problem, they're not going to set up every single possibility. They're focusing purely on the acrylic in the question, okay? So another thing to note about this is that these are percentages. A percent cannot just function by itself. It's a percent of something. So when we're writing this, you have to be really careful about the total amount of the right-hand side. So I'll show you what I mean about that. So I'm going to just highlight or underline the parts that are relevant to the part we're looking at. This first blend, the standard, is 30% acrylic. The deluxe is 9% acrylic. And we want our total pounds, the amount we're going to use, we're going to be wanting that to have a at least 20% acrylic. Okay, so if X is the pounds of standard blend and Y is the pounds of deluxe blend, X plus Y is going to be the total pounds of yarn. Okay, so we're going to need that for that right-hand side because, again, a percent cannot just be by itself. It has to be a percent of something. So for the first part, we're saying that in the acrylic inequality, we're going to have 30%. I'm going to write that as a decimal because that's typically how we deal with our percentages. So 30% as a decimal is 0.30. So 30% of that number of pounds of the standard blend will have an acrylic. That's going to be 30% acrylic. Plus we have 9% acrylic for the Y, that part there. That's the deluxe blend. At least means we want to be greater than or equal to, and we want 20%, not just 20%. You can't just put 0.20. That doesn't make sense. It's 20% of the total yarn needs to be acrylic once we're done. So that's going to be the X plus Y. So we're going to have to manipulate this inequality a little bit to get it in a form where we can graph it. So first thing I'm going to do is distribute that 0.20 on the other side. So that's going to be 0.20x plus 0.20y. I'm going to move everything to one side. So I'm going to subtract 0.20x over to the left. So that's going to make this 0.10x. And then plus, oh, actually, it's going to be minus. Hang on just a second. We're also going to subtract the 0.20y over, but we're subtracting it from 0.09. So that's going to be negative 0.11y. And that's going to be greater than or equal to now 0 because we've moved everything over to the left. So notice that is the simplified version of that inequality. Another thing you might want to do is multiply through by 100 just to clear out those decimals. If we do that, that would give me 10x minus 11y is greater than or equal to, and 0 times 100 would still be 0. Okay, so that's what we're looking at for our inequality. Our non-negativity constraints, remember we're going to have the x is greater than or equal to 0 and the y is greater than or equal to 0. Okay. Now for the graph, I'm probably going to use y equals mx plus b when I go to try and solve that for the boundary line and get the equation set up, because we don't have, if it's equal to 0, when you look at the boundary line, remember that's going to be an x and a y intercept of 0, 0. This is going through the origin. So I'm going to try and solve this for y. So we would subtract over the 10x, divide through by negative 11. So that's actually going to make this positive 10 over 11x. And then notice that our y-intercept would not actually look like it's there, but it's a plus 0. Okay, so it probably just is easy just to count by tens, or not tens, by ones here. But like I said, there's so much to mark. You're welcome to just mark every other one and look like you're counting by twos, whatever works for you. Oops. And I need to not write and talk at the same time. So this is 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I'm going to go to 15. Same thing on my y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Okay, so 0, 0 is a point on my graph for my boundary line. And then we're going up 10 over 11, and it's positive over positive, so it's up and right. So up 10 over 11, that gives me this point right here. I could do that again. I could go up 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Just nice sometimes to have another point to help you draw your line. Okay, and at least remember meant greater than or equal to, so that is why I'm drawing a solid line. Okay. All right, so let's go ahead and figure out which direction we're shading on this, because we already know that first quadrant means shade to the right of this line and above this line. So when we look at the test point possibilities, you can't use 0, 0 here. So maybe I'll use 2, 4. Just picking a random point that's not on my line. So 2, 4 is this test point right here. We plug that in. We want to plug it into our inequality. I'm going to use this version. You can go back to, I wouldn't go back to the original here because you got all of this x plus y and this parentheses, but you could go back to the decimal version or the line above that. You know, you have some options here. 10 times 2 minus 11 times 4 greater than or equal to 0. That is going to be 20 minus 44. That's going to be, let's see, 20 minus 44. Is that negative 16? No, negative 24. Negative 24, not greater than or equal to 0. That is false. Okay. So that means this whole upper, remember this is above this point. So this is the upper half plane. That is all false. So we're going to be shading the opposite side. So this half plane below. And we have to remember to stay above our y-axis and to the right of our x-axis, because that's our non-negativity constraints. So we're going to be shading in everything in between here. And remember, this goes on forever in this direction still, to the right. We just don't shade beyond our graph. Okay. And I didn't draw them in, but remember, you can add in, because they'll probably have you do it on my math lab. You need to show the boundary line for the x greater than or equal to 0 and the y greater than or equal to 0. So it's just highlighting those as a bold boundary line, since they are equal to, for both the non-negativity constraints. Okay. Hopefully that was very helpful, and we'll get you started on your homework. Good. Thank you very much.